Hello, I'm Barış from METU Formula Racing's aerodynamics team. Today, I've set up a simple demonstration to show how Luminary Cloud has helped us accelerate both our analysis time and improve our accuracy. I've imported one of our discarded front wing designs into Luminary. This is a half geometry model and I've placed a rectangular far field around it. Far field is a great tool provided by Luminary that lets you usually create an enclosure volume around your geometry. I've named the bottom face as ground and the left face as symmetry. I've also labeled the fluid contacting surfaces of the geometry as the wing. For the sake of keeping this demo simple, I'll scope the entire wing as a single entity. However, for more precise analysis, it's important to label each airfoil and end plate separately. This gives you better control over mesh quality and ultimately results in more accurate CFD results. Luminary has several smart features that help you spot mistakes faster and improve solution quality. For example, the silver faces warning shown here flags high aspect ratio faces in my geometry, while such faces like end plate thicknesses or airfoil trailing edges are unfortunately unavoidable in our designs. It's great to have this feedback. In this case, I'll simply dismiss the warning and move on. Since Formula Student regulations limit our maximum speed to 120 km per hour, I can safely set the fluid properties as incompressible with constant density. Next, I'll set the ground as a moving wall to simulate the vehicle moving forward. I will also add a body frame, which defines an origin point for the solver to understand the vehicle's orientation. It's important to follow the tooltip's guidance. Set the X direction to point forward and Y direction to the right. If we were to calculate moments, this frame would act as the center of rotation. Since we don't have any rotating components like propellers or spinning wheels in this model, I'll skip the physics related to rotating parts. Had this been our full body vehicle geometry, I would have set the wheels as rotating parts in this menu. Now, moving to boundary conditions. I'll assign the left plane as a symmetry plane. The ground and wing surfaces will be set as no-slip walls. The far field represents the edges of our enclosure, and by setting proper flow conditions here, I avoid having to assign separate inlet and outlet conditions. For simplicity, I'll use zero gauge pressure and set atmospheric pressure under fluid properties to minimize solver complications. Next, let's dive into mesh settings. I'll keep the mesh fairly coarse to shorten the demo time and reduce the cell count. First, I'll set the global minimum cell size to 2 mm. Then, for surface mesh settings, I'll adjust it to better capture the curvature around the airfoil profiles, setting the minimum surface cell size to 8 to 4 mm. Now, the critical part for any CFD application, setting up boundary layers. I'm using an online Y-Plus calculator to determine appropriate boundary layer thicknesses, stretching factors, and initial cell heights. Since we are using the runs SSD turbulence model, I aimed for a y plus value close to 1 around the wing. For simplicity, I use the camber height instead of the chord length to define my boundary layer settings. Though for higher fidelity work, it's better to use the chord length as recommended by literature. Also, because I labeled the entire wing as a single surface, the boundary layer will be uniform across it. Again, for real-world accuracy, each airfoil should have its boundary layers calculated and set individually. For the ground, to reduce the number of cells, I'll allow a slightly higher Y plus value, up to 4, which is still within the SSD model's acceptable range. I also adjusted the upstream length based on the wing's distance from the far field's inlet and paste those settings into Luminary. To further refine our mesh, I'll set up two refinement regions close to the wing. Cells inside those volumes will be smaller than the global mesh size, ensuring better resolution around key aerodynamic surfaces. Now we are ready. I'll hit start mesh, and in just a few minutes, Luminary generates around 40 million cells. Now let us inspect the mesh quality. As expected, the boundary layers have been implemented pretty well, and overall orthogonal quality looks good. Of course, in narrow regions like thin trailing edges, the mesh isn't perfect, but that's due to the simplified approach I've taken for this demo. Thanks to Luminary's tools, these issues can be easily addressed if desired without hassle. Now let's proceed to solving. The solution should take only a few minutes again. Due to our simplified and low effort setup, the residuals here are relatively high. However, both downforce and drag forces appear to have converged, so I've manually stopped the solver to keep the demonstration short. If you are interested in seeing Luminary's full potential, I highly recommend checking out the commercial vehicle aerodynamics example available in their library. It demonstrates much better residuals and professional grade results. Another great feature, Luminary allows for post-processing directly within the browser. No need for separate visualization software. I've set it up here to display surface streamlines, helping us visualize how the front wing interacts with the canards, wheels, and side pods had they were implemented in the geometry. In conclusion, Luminary Cloud has drastically improved how fast and accurately we can conduct our aerodynamics analysis, especially if we were to perform a half-body full car analysis. Cloud-based measure and solvers free our personal computers to continue working on other assignments. Plus, Luminary servers are quite rapid, and in several minutes we can get full-body analysis results. Time is perhaps the most valuable resource for Formula student teams after all. Luminary streamlines the entire process, from setup to meshing to solution and visualization, saving valuable time and effort. For a team like ours, where rapid iteration and precision are critical, it's truly a game changer. We would like to wholeheartedly thank Luminary for sponsoring us, and I hope this demonstration gave you a clear insight into our workflow with Luminary.